Hi, and welcome to the virtual version of the atomic spectroscopy experiment. During this video, there will be a few concept tests in which I'll encourage you to pause the video. So please take those seriously. Really do pause the video, think about the question, and then come back. We're going to start with a tour of the apparatus. Okay, so here's an overview of the Gyphon spectrometer. We have a gas source here. So this is a glass tube that is filled with hydrogen gas, and a voltage is being applied between the top and the bottom of the tube here. You can't see the electrodes, they're covered for safety reasons. That voltage causes the hydrogen to become a plasma. It tears the electrons off of the hydrogen, and then that's sort of happening in a continuous process. So when the electrons fall back down onto the bare protons, that's when the light that you can see here is being emitted. So that light is being, let me show you the front part of this. So I don't know if you can see it, there's a little slit there, and I can adjust the width of it with this knob here, but I'm not going to. I've already set it to the width that I want. And so we're going to center that slit on the hydrogen plasma tube, and then the light from that, I think there probably is a lens at this end and another lens at this end, so that forms a collimator, and then that collimated light goes to this, which is our diffraction grating. So that round circle there is actually, it looks transparent, but it's actually filled with a diffraction grating. And then we have this second telescope, which we can move around to look at the light that's being diffracted from the grating. And so to start with, I'm going to line this up straight in the straight ahead direction, which should be the m=0 peak. And I'll see if I can show you what it looks like when you look through the eyepiece of this. So obviously it's not ideal, but you can see over on the right side there is that pink line. So pink is not a pure color, so that's your cue that this is actually several lines being superposed. And you can also see it's a little bit off center. So if I move the telescope slightly to a different angle, it's hard for me to do that while I'm looking at the camera. I'm going to do it with my eye. I can get it better centered now. And in the video camera it looks pretty bright, but when I look with my eye, try to show you what I'm doing with my eye, I can tell that this is not properly centered. So I'm going to shift the whole spectrometer to the left and the right until that gets really bright in my field of view. Let's see if you can tell the difference here. Probably not because of the auto exposure in the camera, but it's much brighter now. We're going to need as much brightness as we can get, because when we go off to see the diffracted peaks, they will be much dimmer. This telescope, the second telescope, has got built into it a way to read the angle that it's at, and this is an important learning experience. It has built into that angle reading thing this extra scale, which is called a vernier scale. So if we look right now, the main reading is from the leftmost mark on this brass colored scale, and I would say that right now that's at about 329.2. We can get the exact tenths of a degree using the vernier by looking at which one of the 10 markings on the brass colored scale is exactly lined up with one of the markings on the silver colored scale. And I would say that it is probably the second marking, which means that it really is 329.2. Now, in principle, this should be the straight ahead direction, so it should be closer to 0. So I could zero it, but instead what I'm going to do is accurately measure where the center of this line is. So let me do that right now. As I was trying to measure accurately the center of the m=0 line, I realized that pushing this back and forth is really too crude. And when you're using a nice instrument, often the designers of the instrument have provided a fine adjustment for you, and in this case it's down here. So when I turn this knob, I don't know if you can see that that's moving this telescope by small increments. So that's the fine adjust. So I will use that to get the exact measurement. Okay, so there's a crosshair inside here that I can't pick it up with the video camera, but I centered that crosshair on the m=0 line, and then I used the vernier to read it, and that line is at 324.1 degrees. So now I'm going to move this to the right to try to pick up the m=1. So let me see if I can show you. Right now I'm on the violet line, which is actually the closest one in, but it's also pretty dim. So let's see if we can see that. I think I got it. Yeah, this is on the aqua. The color is being distorted a little bit by the video, because in the video it's looking really blue, but it's actually violet. So it's interesting that the color sensors on the video camera are different from the color sensors in my eye, because it's a completely different color when I look at it with my bare eye. So you'll have to take my word for it that this is actually the violet line. That's the m=1. I will measure the exact angle for that later. Let me just, for now, I'll show you the other lines. There is the aqua colored line for the m=1. That's at a somewhat bigger angle. If I keep going to even bigger angles, I should get to the red line right there. There, whoops. Banging my lens on the eyepiece. Where is it? There. Okay, so that's the red line. And again, to see those different lines, I was moving, let's say, to about here to get the violet, and here for the aqua, and here for the red. I'll get the exact numbers and I'll collate those for you into an Excel spreadsheet. If I keep on going, somewhere probably about here, I'll get the purple line, the violet line for the m=2, the aqua colored line, and the red colored line for the m=2. I'll get those exact numbers for you. Next we're going to set up this Redtide spectrometer from Ocean Optics. By the way, if you want the model number and stuff on this Gyphon spectrometer, I don't know that we have one. It just says it's supplied by Gyphon and George, London, but I don't see a model number on it. But anyway, there's the model number on the Redtide spectrometer. It has a fiber optic cable. There's the end of the fiber optic cable, and I'm going to mount that in this holder. So I'm going to just push it into the end of this holder, which has a little slot in it. I'll push it in as far as it will go, and then tighten up this nut to hold it in place. I'd probably do a little bit better than that. And so now, I hope you can see this. There's the little pinhole at the end where light is going to go in. Can you see that? It's really small. Light is going to go into the fiber optic. So I am going to use this holder to attach the fiber optic so that little pinhole is right in front of our hydrogen source. You can see that there's little adjustment screws here, so I can move this back and forth, and I'm going to start with it centered. We'll see how well that works. All right, now as it says in the directions, I will launch LoggerPro. Give it a minute, and it has indeed detected the spectrometer, as we can tell from this colorful display. Then continuing to follow the directions under experiment, I choose change units, spectrometer 1, select spectrometer mode. I want intensity, because that's what we're going to be doing, measuring intensity, not transmittance. And I'm going to set the sample time following directions to 50 milliseconds. The wavelengths moving to 0, samples to average to 20. So that should be good now. Now if it's gotten rid of my beautiful spectrum. All right, well, that's a little bit unfortunate that I got rid of the spectrum. I can't figure out how to put it back. But it still does have the wavelength written down at the bottom. And now it's relative intensity here. So if I click on collect, let me first make sure that our meter, our fiber is centered properly. Good. And now I will click collect. And what it's doing now is collecting 20 spectra and averaging them together. At least that's what it should be doing. Although, yeah, it is live. It's changing very slightly. All right, so concept test. What we're plotting is intensity on the vertical axis versus wavelength. And there's something that's not so great about this spectrum right now. So, in fact, there's maybe a couple of things about it that aren't so great. So think about it on your own and pause the video and then come back and tell me what you think are the things that are not so great about it. Okay, so one thing that's not so great is that this peak is squared off at a value just below 1.0 on this relative intensity scale. That strongly suggests that the sensor has been maxed out. And so that's usually not what we want. We usually want to see everything being read at a not maxed out value. So think about it on your own. How could I fix that particular problem with this? How could I keep that from being maxed out? Again, pause the video and then come back. The way I could do it is by intentionally moving my fiber optic off center a little bit. So I'll just shift it slightly off center. And now if I stop the data taking and restart, I'll choose erase and continue. It's still squared off there, so I got to move it further off center. And now it's really weeny, so I went too far. So let's go back. Somewhere in between, maybe there. This would be helpful to have a partner for this. Maybe I can reach around and watch live. That's too far. It's a very coarse adjustment that I've got here. Oh, that's just about perfect there. All right, so let me stop this and restart it. I'm going to turn the lights off, just probably we don't need to, but just to do it, I'm going to erase the last data. And there we can see this one beautiful sharp peak. And then there were some peaks over here, but they're gone now. So in order to get all the wavelengths accurately, I'm going to have to make measurements with the fiber in different positions. So for this one, I've got plenty of data to measure this accurately. I'm going to stop the collection. And then you can maybe see down in the corner here, as I move my mouse, it's accurately reading what the value is. And so let's see, if I click, do I get crosshairs? No. Unfortunately not. But I can position the mouse right at the peak of that peak, and that's at 654.3 nanometers. The vertical scale is not very meaningful because we haven't calibrated the spectrometer. So it probably has a sensitivity that depends on wavelength, and so if we wanted to quantitatively compare these peaks, we would have to calibrate it with something that had a known intensity at various different wavelengths. So we can only roughly get the intensities, but we can accurately measure the wavelengths. All right, so now that I've got that really big one, I'm going to go back and recenter this, and we'll allow it to saturate that biggest peak, but this will allow us to measure the littler peaks better. So, interesting. So, I can already get this next biggest peak here. That is at, try to get it accurately, 484.6 nanometers. Then things drop way off in intensity. This next one is at 432.4 nanometers. There's one at 409.3, one at 395.9. Now I wonder whether we can adjust the scale on this. I'm going to stop the data taking. Let's try changing the scale. What if I type in 0.1 on the scale here? Yeah, that helps a lot. So now I'll just remeasure these last three because I can see them more clearly now. 432.8, 408.8. I'm going to change the scale to 0.02. 0.02. There we go. Now we can see them much better. 408.6. 398, no, 395.8. This one maybe is questionable. 387.4. There's a bunch of other stuff over here that I want to point out to you. I'm not going to measure that. Let me change the scale back to, let's say, 0.2. 0.2, not 0.02. Come on. 0.2. So there are other peaks over here, and I would like you to be thinking about where are those coming from. So the ones that I'm going to bother to measure are this really big one and the peaks that are longer wavelength than that, but the peaks that are shorter wavelength than that, to the left of that really big one. But there are also some quite substantial ones at longer wavelengths. I'm not going to measure those quantitatively. Oh, sure. What the heck? Let's go ahead and do these. You may or may not actually want these, but this one is at 776.3. This one is at 843.7. And this one is at 925.6. So I encourage you to think about where are those coming from. Come on. I want to change the scale. Let's go to 0.02 again. And you can see there's a bunch of sort of crappy things here. There's the main peak, and to the left, to shorter wavelengths, there's a bunch of little stuff here. which I'm not going to bother to measure. There's also some little things in here. I want you to think about what could those be due to. Okay, so next we're going to compare qualitatively the spectra of hydrogen, carbon dioxide, nitrogen, and helium. You can see qualitatively, just looking with the camera, that they're pretty different. I'm going to turn off the room lights, and I'm going to put this diffraction grating glasses right in front of the camera. Okay, I've got the room lights off, and I have set the exposure to manual, so it'll be a fair comparison for everything. So here's the view of hydrogen. We can get it all in there. And then for comparison, here is helium. And then here is nitrogen. There's nitrogen. And then finally, carbon dioxide. Okay, so now we're doing the bit with the quantum dots. You can see we have these 4 vials that, let me get them against a white background for you. They all look about the same. So in fact, I would say the 3 on the left look essentially the same. They're all kind of light pink, and the one on the right is maybe more yellowish. But they're almost colorless, just very faintly colored. Here I've got some little LED lights. So let's start with, let's try to find the red one. Okay, so there's the red one. I'm going to shine that up through each of these. Maybe I'll turn off the room lights, so this will be a little more dramatic. So there's the red one in the rightmost, there, there, and there. I think hopefully you can see it, that basically all we see is just red light from those. So now let's try to find, okay, here's a yellow. I'll try that one. So there's yellow on that, just looks yellow, yellow, yellow. Ooh, this one is different. Can you see that? I'm gonna, okay, I've readjusted the exposure on the camera. So there's yellow, 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 and something different happens here because you can see a kind of a reddish cone of light where the LED is illuminating it. Whereas on the other ones, it's all yellow. Now let's see what else we can find. Let's try to find a green one maybe. There's blue, that's white, there's green. So let's try it with green. This one is just green, green, green. And this is a little bit harder to see, but there is some red in addition to the green. But for the other ones, I'm only seeing green. Now let's try blue. Here's blue. So that's blue there. I don't know if you can see it, but there's a faint green beam in addition to the blue. I don't know if it's better with the room lights out. Maybe a little. Faint green in addition to the blue. Here there's orange in addition to the blue, and here there's that red. Turn the room lights back on. So there's just blue, there's a faint green, faint orange, and a pretty bright red. And then finally we'll do this one, which is the ultraviolet one. So here, just, I don't see anything special going on there. Maybe with the room lights off. Oh yeah, with the room lights off I can see this one is green, yellow, orange, and red. So the ultraviolet, I get these different colors coming out. Maybe if I'm further away. Yeah, that's green, yellow, orange, and red. And let's contrast that with, let's say, the yellow, which is just yellow, 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 and there's the red there. Okay, so for the last part of the data taking, I'm just going to show you here what I'm going to do. I'll take the ultraviolet LED and shine the light in, and while I'm doing that, I will hold the fiber optic off to the side to collect the spectrum, and I will send you guys the spectrum.